Today, we want to look at applications of integration, some applications of integration, not all of them, just some of them, and more than just today. Let's recall the way we want to think about integration. So integration is multiplication, but one of the factors is variable. Integration is multiplication, but one of the factors is variable. Remember that multiplication is repeated addition. That is, multiplication is a shortcut when all of our terms are the same. Multiplication is repeated addition. We use it when all the terms are the same. We want to think of it as something that we get to do. But one of the factors is variable. So in multiplication, or if we can't use multiplication, we have to stay at addition. So in that sense, integration is addition. Integration is addition. Sometimes we think of integration as accumulation, but it's just addition. We're just adding things up. We want to multiply, but one of our variables, one of our factors is variable. So we have to stick with addition. So in the category of thinking about integration as addition, this is when we start getting this part of the Riemann sum, the sigma part of the Riemann sum, where we add up I goes from 1 to n, f at xi times delta x. In this construction, we're using area equals length times width, and we're assuming that the length is constant for some part of the width. Here we are, this is the constant length, and this is the width that we're applying, so we can drop it back to multiply. But since not all those rectangles are the same size, we have to add them up, because integration is addition. The other important thing that goes with integration is that we are switching from a discrete sum to a continuous sum. So the definite integral represents a continuous sum. So this is, rather than a discrete sum, we have a continuous sum. So the continuous part shows up when we take the limit as n goes to infinity in our Riemann sum. That's the continuous part. The Riemann sum is the addition part. When we let n go to infinity, that's when we switch things over to a continuous sum. And we get the definite integral. So what we want to do now is look for scenarios where we're trying to do a calculation with multiplication, area equals length times width. But one of the factors is variable. The length keeps changing. The way we work the problem is to assume that the variable length, assume that it's constant for a little while, so that we can use multiplication, and then we just add up all of those terms. Same strategy, all the problems. What makes these problems easy is that we're only going to be using one variable. What makes these problems difficult is that we're only going to be using one variable. So we have to put everything in terms of that variable. That's the sneaky part for this process. Let's look at a problem, what we've done before. Let's consider this region. I'm going to just use this parabola because I always use this parabola. Y equals x squared. And I'm going to have the horizontal line y equals, how about 4? So this happens at x equals 2. All right. Let's suppose that the area we want to find is bounded by the y-axis, the graph of y equals x squared, and the line y equals 4. So when we first start doing these problems, we know that the definite integral is going to give us the area under a curve, that is below the curve and above an interval on the x-axis. But what if we want to find some other area that's not bounded by the x-axis? Let's see, what color should this? I think this should be orange area. What if we want to find that? Let's consider the region. Let's see how we would describe this. Consider the region bounded by the graph of y equals x squared the y-axis and the line y equals 4. So we want that orange shaded area. We know that we can use a definite integral to solve this problem. We could say calculate the area under the x squared and above the x-axis and subtract that from the area of the rectangle from which this region is cut. But we want to set the problem up differently. So one example, so note. We could find the area below the x-axis. So if we integrate from 0 to 2, x squared dx will be the area below the graph of y equals x squared and above the interval from 0 to 2 on the x-axis. Once we have this area, we could subtract that from 8, and that will give us the orange region, the region bounded that above above the graph of x squared and below the line y equals 4. But we want to set the problem up originally in the area that we're looking for. This would be going about it kind of in a roundabout way. It would be effective, but effective is not what we're looking for. We're looking for options. We want to practice the skill of constructing this definite integral. So here's what we're going to do. We're calculating an area, and we know that all we need is length times width. Area in calculus class is always just length times width. That is the only area you need anymore. Pi r squared, feh. 1/2 base times height, teh. A Jedi craves not these things. Length times width, that's all we need. Length times width, this is the way. So here's what we're going to do. Let's take a look at this region again and not shade it in so that I can draw a rectangle, because we're going to use a rectangle. Come on. Once again, the goal is not to find the area. The goal is to learn a technique that will work more generally. This is still angled somehow. All right. So here's what we're going to do. What we're going to do is we're going to look at a slice of this region, because we know that area is equal to length times width. All we ever need, area, is equal to length times width. So I'm going to draw a piece of length times width in this region. I'm going to look at this region as a bunch of slices. I'm going to start by slicing this way. I'm going to slice vertically. So let's look at a vertical slice. The area is length times width. I'm going to say that the width is some small change in x. So here is the width, and that's going to be some small change in x. What we're going to do is we're going to slice this thinner. So instead of looking at the area below the x-axis, the traditional place to look for your definite integrals, I'm going to say, nah, it's between below -4, but above the x squared. The length is going to, the top of it is going to be at 4, and the bottom of it is going to be determined by the graph. So here is the length. Top's at 4, and the bottom is at the function. The width is since the width is being written as delta x, I need to write the length in terms of x. X is my delta variable. That's the one that's getting thinner. So since the width is written delta x, so we need to write the length in terms of x. The connection between the horizontal and the vertical is going to be the function y equals x squared. So at this, we want everything in terms of this x here. So here's x. And because we're on coordinates, this distance is y. So we can see that the length starts off at the function and goes up to y equals 4. From the x-axis to the function is the length y, and the total distance from the x-axis to 4 is 4. So I can write that the length is equal to a total of 4, then subtract the y. So 4 minus y. The total is 4. One piece is y, so the other piece is 4 minus y. So the area of that slice is now the length, which is 4 minus y. Oh, sorry, 4 minus x. Oh no, 4 minus y, sorry. I just didn't finish talking about the length. I don't know if this is a more coffee problem or a less coffee problem, but I know what solution I'm going to apply. So the length is 4 minus y, and this is no good. I just saw up here, the length has to be in terms of x, but we have this connection, y equals x squared. So I can write the length as 4 minus x squared. So the length is going to be 4 minus x squared, and the width is still delta x. Now I have an expression for the area of any vertical slice in the region that we're looking for. Now what we need to do is add up all the slices so that this will become a definite integral. So now we need to add up all such slices, or all the areas of the slices, and then let the number of slices go to infinity. So we're going to make a Riemann sum. So let all slices go to infinity. So I'm going to take all the slices that have the form 4 minus x squared. The width is delta x. I'm going to add up all of these slices. Because I'm going to index the slices, and then we'll let the number of slices go to infinity. This is the step that we're almost never going to write. Poor Riemann. Great idea, never gets written down. But this is the thinking that's always running behind it. What we really want out of this is the definite integral. In the definite integral, we're going to integrate the length, which is still 4 minus x squared. In the continuous variable, when we vary x continuously, we go from a discrete delta x to a continuous dx. And the definite integral is set up with x values. So we integrate all the x's where we see a slice of the region. And the x's start off at 0, and the x's end at 2. So we integrate from 0 to 2. I'm going to label these as x equals 0 to 2. So we integrate over all the x's where we have a slice. So we integrate over all the x's where we have a slice of area. And that's from 0 to 2 in this case. Any questions? So let's write down this integral and then notice something about this integral. So let's take a look at this integral. We got the integral from 0 to 2 of 4 minus x squared dx. So if this looks suspicious to you, it totally should. Because at this point, you should be like, oh, dude, isn't this just the plan that we had before? Subtract the area under the x squared from the rectangle. So right now you're thinking, dude, isn't this just subtracting the area Isn't this just subtracting the area under the x squared from the rectangle? That is our original plan. And the answer is yes, it absolutely is. Because if we split this up, we can split up the terms and integrate from 0 to 2 of 4 dx, and then subtract the integral from 0 to 2 of x squared dx. And the integral from 0 to 2 of 4 dx is just 8, the original rectangle. And we're subtracting the integral that you proposed in the beginning. It's good, it makes sense that this makes sense because we've got this rectangle, and the rectangle is split into two regions by this parabola. We've got the area below, which I previously labeled it with this blue color, and the area above, which is the one that we're looking for. So mechanically, we're just subtracting from the area. So why all this interest then? Well, let's look at it another way. The reason that we want to point out that this is our original plan is because we always want to acknowledge that there are many ways to go about a lot of these problems. The reason that you don't want many ways to go about a problem is that because it means that you have to choose one way over another. That's why people are always saying, can't we just do it the other way? But you got to remember that when people make that argument, they are arguing against knowing something. There's something that we could know. Let's not know that because ignorance is bliss. But we're not in school so that we can be blissfully ignorant. We're in school so that we can know things and become miserable. That's the goal. So what I'm going to do is I'm going to slice this the other direction. Instead of looking at this area as a bunch of vertical slices, a bunch of thin rectangles standing vertically, I'm going to look at this as a bunch of flat rectangles stacked horizontally. And kind of change how we view the problem. I'm switching from a delta x slice to a delta y slice. We're still calculating area, and so the only thing we ever need to calculate an area is length times width. Area is length times width. I'm going to call the one that's becoming inthined the width. So the width is delta y. The width is some small change in y. So the length is now some length in x. So here is the length. Area is equal to length times width. In this case, since the width is delta y, we need to write the length in terms of y. Since the width is delta y, Since the width is a delta y, we need to write the length in terms of y. So let's go back to our diagram and notice that if we pick this point where the rectangle intersects the graph, here's the distance x, and the distance y is this vertical distance. So we can see that the length of this rectangle is just equal to x, but this isn't no good because we need the length in terms of y. The length is equal to x, but we need the length in terms of y. So once again, we will appeal to our equation that relates x and y. Since y is equal to x squared, this means that x is equal to the square root of y. So now I can write the length as the square root of y. So the area of the slice is the length, which is square root of y, times the width, which is delta y. Now I form a Riemann sum, and we just need to add up all the areas with values of y. We just need to we need to integrate over all the values of y where we have a slice. Integrate over all the values of y for which we have a slice. So we just need to integrate over all the values of y for which we have a slice. So we have a length, we're going to integrate. We have a length, which is the square root of y. The delta y becomes a continuous dy. And then we just go back to our graph and see our y values start off here at 0, and our y values stop at 4. So we're going to integrate dy from 0 to 4. So this is our integration process. Notice that we have done no calculus today, except for write the integral symbol with a dx or a dy. It's not about doing the calculus, it's about setting up the integration that we could do to find the area. What we're trying to do is understand integration by setting up definite integrals. This one we could easily do by hand, but let's find out if we get the same thing. Let's do a math 9 of the square root of y with respect to y from 0 to 4. So it looks like 5 1/3. Let's integrate the other one we had, which was a math 9 of 4 minus x squared with respect to x from 0 to 2. 5 1/3. If you're concerned about what's happening in the 544 way down here in the what's this, tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, in the 10 millionth spot, that's because your calculator is rounding things off. So if you show up into court, someone might say, look, see, the original way with the subtraction is better because it's closer to the actual value out here in the millionth spot. Then the reasonable argument is going to be saying, you're using technology from the 90s. There's going to be some round off error. And what you're doing is you're worried about the dollar, like buying a $2 cup of coffee versus a $3 cup of coffee when you have $5 million in your pocket. So, you know, get over it. Billionaires don't become billionaires because they make coffee at home. That's not how money works at those quantities. You know what I mean? All right. So tomorrow we're going to look at more examples of slicing things up and making calculations on those slices. We want to be familiar with. It's not that we want to be able to find areas with bounded by functions just one way or the other. It has to be both. It has to be both because we are limited by this single variable business. So if you're just like, oh well, I would just always integrate in terms of x. You can always integrate in terms of x until I make things vary up and down. So I'll say, not find the area, but find the mass of this region when the density varies with respect to y. If the density varies with respect to y, you have to integrate in that direction because we only get to use one variable in single variable calculus. Any questions? Comments? Snide remarks? All right, that's it for today. I will see you on tomorrow when we'll actually do that. I'm going to give this thing variable density. I'll see you all on tomorrow, and thanks for playing.